Hello everybody, today we'll continue the chain growth polymerization and we'll continue the description of different steps. As I said before, we have 4 steps for chain growth polymerization: initiation, propagation, termination and transfer. And now I will continue with the propagation after talking last time about the initiation. The propagation step. This step is a very important one because during this step, macromolecules grow by chain addition of monomer molecules to the newly formed PM radical, which is the first primary active center. Upon reaction with a fresh monomer molecule, the active center, the radical, is transferred to the last generated monomeric unit, and so on. Otherwise, monomer take the active center. The last monomer take the active center. So if the propagation continue, we have PM2 plus M, we have PMMM. So the last M will take the radical till the end of polymerization. The propagation has a constant rate during all the polymerization process. In fact, propagation is a very fast step, so that it's an exothermic phenomenon, and the reaction sometimes may run out of control and even sometimes can become explosive. So we have to take care precising the duration of polymerization and the temperature of polymerization to avoid having explosion. Example of propagation, if I take the example of vinyl monomers, so here I have the first or the primary active center. The radical will attack the monomer, so we'll have the addition and you have the propagation. And here, as I have a substitute over the CCC, so the addition will be head to tail, because like I said before, for the addition head to tail or tail to tail, here the addition is controlled by the fact of the presence of the substitute, because we need to have the most stable radical in the medium, because as you know, the stability of the radical increases if the substituent has inductive or resonance possibilities. Then the propagation continue by addition of n other monomers. So we'll have here the active chain, what we name a propagating active chain. Now concerning the termination, this step implies the collision of 2 growing free radicals. The possibility to have collision between these 2 propagating active chain is less higher or less important than the collision to a monomer, but it exists. In fact, the termination can occur by 2 different processes. The first one is the combination. In the case of absence of steric constraints, the collision of 2 macromolecular free radical or propagating active chains result in their combination, and you will have formation of one big molecule or macromolecule. And the second way of termination is by disproportionation, where we have formation of 2 molecules. The mechanism of this disproportionation or termination step by disproportionation occur in 2 half steps. The first one corresponds to a beta elimination under the effect of collision, and thus we have formation of H radical and formation of a molecule having double bonds. So we have generation of new monomer, big new monomer. And the second one correspond to the combination of propagating active chain with the ejected H point or H radical, and we will have formation of dyed chain. The last step is the transfer step. Here we have the propagating active chain. We have transfer of its active center to a transfer agent. So we have formation of dyed chain and formation of new radical. This new radical will attack a monomer. If this radical has no activity or no reactivity through the monomer, so we'll talk about termination. But if this radical has reactivity through the monomer, so we'll have new initiation, and here we talk about transfer. The transfer agent, it could be which molecule present in the medium. It could be the initiator, the monomer, the polymer, the solvent if we have solvent in the medium, or it could be a special transfer agent. So here, if the monomer, the new radical formed has reactivity through the monomer, and I have new initiation, and thus I have transfer. In this case, the number of active center still constant in the medium, but the length of polymer chains changes or varies, because we have formation of a dyed chain with specific length, and I start new chain from the beginning. So the length of these polymer chains varies, and thus we have higher dispersity in the medium. So the transfer step leads to increase the dispersity in the medium. So this is variation of dispersity. It's a problem for the application, because if the length of the chain or polymer chains vary, thus their mass varies, the dg varies, the mechanical properties vary. So we have big influence on the application. So if I consider the different transfers that can occur in the medium during polymerization or radical polymerization, if I consider first the transfer to initiator, and I take the case of hydroperoxides or peroxides, here we have formation of dyed chains and regeneration or formation of a radical, and this radical surely has ability to or reactivity through the monomer. This step can remind you about the induced decomposition when we talked before about the initiation, and we said we have loss of radicals due to induced decomposition, and this induced decomposition is due to the attack or whatever which active propagating chain or whatever which radical present in the medium. So the transfer to initiator leads to the consumption of initiator molecules, and thus decrease the initiator efficiency. If I consider the case of ABN, the ABN is special, does not undergo transfer reaction, so that's why it's much widely used than the peroxides. The second transfer could take place to monomers. So if I consider here the case of acrylates, more specifically polyvinyl acetate. So here I have the substitute, which is acrylate. I have the propagating active chain, and I have my acrylate monomer. So if this radical will take one hydrogen from this monomer, surely it will take the most label hydrogen. So here the radical will take the hydrogen on the methyl group, and I will have formation of dyed chain, and I have formation of a new radical in the medium. And this radical, if has the ability to react with the monomer, and I have new initiation, I should pay attention here. I have radical, so the polymerization can be initiated from the side. Here I have still have the double bond of the monomer, so the polymerization also can continue from this side. So the transfer to monomer leads to formation of dyed chain, so to the death of propagating chains, and I have new initiation, and as I have new initiation, so I have variation of the dispersity. The third one, or the third case, is the transfer to polymer. So if I consider also the same acrylate propagating chains, here the transfer to polymer, this transfer could be to dyed chain. Already one propagating chain died, so this radical will take the hydrogen on the methyl group, like in the case of transfer to monomer. So I'll have death of this propagating chain, and I have formation of new radical, and this radical is over a macromolecule, so it's macro radical because here it was a dyed propagating chain, dyed polymer chain. So here it will have surely reactivity through the monomer, so I will have new initiation. Also, the transfer to polymer, it could be transferred to other propagating chain. So this radical could be transferred to another propagating chain. So I will have here a surely dyed one, like this one, and I will have formation of double radicals. So in both cases, if I have transferred to dyed polymer chain or transferred to propagating active chain, I will have formation of branched polymers because the polymerization will go from different points or different sites. Considering the case of transfer to solvent, so if from the beginning in the polymerization medium we have solvent, initiator, and monomer, so here as I have solvent, I have the possibility that the propagating active chain transfer the active radical to the solvent. So we have a formation of dyed chain, and I have formation of new radical, and this radical, if this radical has the ability to attack a monomer, so I will have new initiation. If this formed radical has no reactivity through the monomer, so I will have here like termination. So we have dyed chain, and I don't have new initiation in the medium. So we have this transfer to solvent if the solvent has an easy living group. So as examples, if I have the C6H6 or ROH or CCl4, here I have an easy living group, so I can form as a point. So to avoid this transfer case, the solvent should be well chosen during polymerization. Because if I don't want to have a high dispersant in the medium, I should limit the possibility of transfer steps. The last case of transferring is transfer to special transfer agent. All previous transfer cases are considered negative for the polymerization process because they lead to large variety of molar mass and length of polymer chains, and thus they increase the dispersity in the medium, and as I said, it's so bad for the applications. But if we want to control the molar mass, means if we want to control the degree of polymerization, so here transferring become positive because we add in the polymerization system, or in the polymerization medium, we add specific or special transfer agents, like here, for example, in the case of controlling the degree of polymerization of polydienes, we can add the thiols. Here we have the mercaptans, and the activated radical or the active center will take the hydrogen from the thiols, and we will have a dyed chain, and we have release of a new radical which have reactivity through monomers and reinitiation in the system. But here we control it. So the transfer to special transfer agent, it's positive one because when we want to control the molar mass and the dispersity in the system. We have also more than mercaptans. We have the sulfide, disulfides, and halides, which could be used as special transfer agents. How it works experimentally. At the beginning, for example, we have our medium containing the monomer and the initiator. If we start polymerization for a specific time under heating, For example, let's say 1 hour, and we know for 1 hour we will have molar mass of around, let's say 5,000 gram per moles. So at this moment, we add our special transfer agent. So in the medium, we will have the remaining monomer which should not react yet. We have the initiator which is not decomposed yet. We have the dyed chains formed due to the transfer of the active radical from the propagating active chains to the special transfer agent, and thus we will have new initiators. So whatever the remaining initiator or the new initiators, now they will start the polymerization again. So we have till this point polymer chains having specific molar mass, specific length. So now if we continue the polymerization for another 1 hour, for example, and we will add again the special transfer agent, we can continue doing this till the total consumption of monomers in the medium. By this way, the transfer, as I said, is positive because I'm controlling the mass that I want. At the time that I know I'm reaching desired molar mass, we will add the special transfer agent, and we will continue doing this till the end of polymerization. What are now the factors that influence the radical polymerization? In fact, there are two factors. We have the first one is the inhibition, where inhibitors play a role delaying the starting of the polymerization. In fact, polymerizations, once we have inhibitors in the medium, it's prevented to occur normally. So polymerization can't start before consumption of all the quantity of inhibitors present in the medium. So if I have inhibitors in the medium, these inhibitors have high reactivity through the radicals, so they will take the radicals in the medium, or they capture all radicals present in the medium, especially the initiator one. So I can't start the polymerization before consumption of this quantity or the presence, the quantity presence of inhibitors in the medium. In fact, ideal inhibitors should have high reactivity to deactivate the initiator radicals, and this just positive in the case when we want to preserve or to protect or to prevent the autopolymerization of polymers. If you remember last time, I talked about the adding of specific stabilizers to prevent the autopolymerizations of monomers during storage. These stabilizers are inhibitors, which are molecules having high reactivity to deactivate initiator radicals, so to avoid any polymerizations. When the autopolymerization to deactivate any monomer after collision, having any radical monomer formed after a monomer collision. The second factor is the retardation. Here we have retarders, which delay also the rate of polymerization. If you want to describe these two factors over a graph, here I have the variation of polymerization rate as function of time, and I have, for normal case of polymerization, I have my specific rate which increases with the polymerization time. Now if I have inhibitor in the medium, as I said, inhibitors will take all radicals present in the medium, so I can't start polymerization before consumption of the all quantity of inhibitors in the medium. So if I have inhibitors, once the quantity is consumed, then I start the polymerization, and the polymerization starts in the same rate as the normal case. It's just delayed in time, in starting time. If I have retarder, the polymerization starts from the beginning, but the problem, this is the rate of polymerization which decreases because of the presence of retarder in the medium. Some molecules or some reactants combine the two types of behaviors. Start by inhibiting completely the polymerization, so I have delaying in time, and then they play the role of retarders, so the rate of polymerization also it's influenced. So according to the kind of reactant present in the medium, we can have inhibition, retardation, or I can have a combination of two types of behaviors. Examples of inhibitors and retarders during radical polymerization. We have the oxygen. The oxygen is the most important inhibitor which can be present in during polymerization in the polymerization medium. So if I have oxygen in my medium, the polymerization will not start before consumption of all quantity of oxygen. Why? Because the oxygen will take the radicals from the medium, the initiator radicals, and you have formation of ROO point, peroxide radical, and this peroxide radical will take an hydrogen from whatever which possible molecule present in the medium, and we will have formation of hydroperoxide, and we have liberation of a new radical in the medium which will be able to restart or not the polymerization according to its reactivity to the monomer present in the medium. So here the presence of oxygen influences not just the starting of the polymerization by delaying it, but also it influences the efficiency of the initiator, because we have consumption from part of the initiator in the medium and also creation of initiators. So the real quantity of initiators in the medium during polymerization process will not be well controlled or well known. So that's why during processing we have to make degassing under nitrogen to remove all oxygen from the polymerization medium. Another example of inhibitors, we have the phenols, polyphenols, and aromatic amines, which are also considered as inhibitors for radical polymerization. They react with the radicals in the medium by abstraction of hydrogen and giving rise to aryloxyl radicals whose reactivity is too low to efficiently reinitiate polymerization. So here we have total inhibition of the polymerization till consumption, surely the quantity of inhibitors present in the medium. For example, if I consider the phenol will react with the radical, and I have formation of the aryloxyl radical here in the medium. As natural examples of these phenols, we have the vitamins C and E. Here, these phenols are considered as antioxidant. Why as antioxidant? Because they have high reactivity through radicals. So if we have phenols in the medium, once I have a radical, they will capture this radical and will give stable radical, aryloxyl radical, stable by resonance. So that's why phenols and polyphenols are considered as antioxidant. As I said, I have examples of these natural antioxidant, the vitamin C and the vitamin E, the ascorbic acid, the alpha tocopherol, which is the vitamin E. These two vitamins, the vitamin C has OH, like phenol, and vitamin E has 2 OH. So usually vitamin E is used as regenerator for vitamin C for food preservation. So usually to preserve food, we add vitamin C to increase the shelf life of these foods. Also, we eat much of fruits having vitamin C or containing vitamin C. We take much olive oil having vitamin E to increase the quantity of antioxidants in our body to capture the free radical which could be present in the medium, because as you know, our system is composed of lipids, and if we have radicals in the medium, so the radicals will attack the CCC of the lipids, and we have regenerations of cells, and that's why we can have cancer. So we have to take a big amount of antioxidants to prevent the cancer. Science create or they synthesize two synthetic phenols, which are the butylated hydroxyanidole, BHA, and butylated hydroxytoluene, BHT, sorry. So these two synthetic phenols are used as antioxidant and additives for food and for cosmetics and for oil and oily or fatty materials, fatty foods. If you check your sunscreen, you will find over it that you have BHA and BHC for UV protection, and you can find the sun protection factor SPF, and you have here a certain number or certain value. It can be 10, 20, 30, 50. In fact, this number is related to the quantity of antioxidant present in the medium. So higher the SPF, higher is the quantity of antioxidant and higher is the protection. So if you have a sunscreen with low SPF, you have to apply the cream during short time because the shelf life of the antioxidant is limited. So you have to repeat the application each 1 hour, 2 hours, 3 hours according to the quantity or to the SPF value. The third example is the polyphenols, which are also inhibitors. The polyphenols, as I said once, they are natural polymers and also used as antioxidant. We can find these polyphenols naturally in different kinds of foods, and these foods are essential for our protection of our cells, of our body, of our heart, of our brain from free radicals and from degradation or regeneration of our cells. There are many kinds of polyphenols. We can find the flavonoids, which we can find them in the oil, for example. That's why olive oil, in plus of containing the lipids and the omegas 3, 6, and 9, we have also antioxidants. So that's why the olive oil is very important and it's very healthy. And as you know, surely the olive oil should be preserved in dark bottles to avoid the interaction of light with the CCC present in the oil. So if we have sunlight, the color of the oil will be changed, and also we will have formation of radicals. Sorry. So the antioxidant present in the oil will react with the radicals formed in the medium. So when we eat our olive oil, we lose a quantity of the antioxidant which should be present in this oil. Other examples of polyphenols, we have the lutein, which could be present in all dark green leaves. We can have the lycopene, which is present in the tomato. We have the tannins, which can be found in the tea. We have the beta carotene also in the carrots. We have the catechins, which can be present also in the tea and in the dark chocolate. So all these polyphenols are inhibitors, are so bad for the radical polymerization if I'm doing polymerization, or if they are present in my polymerization medium. But in parallel, they are very important antioxidant to preserve food and to increase the shelf life of our cells. Antioxidant has antioxidant activity, antimicrobial effect, anti-aging activity, anti-inflammatory activity, cardioprotection activity, and also protection against UV irradiation, and also prevention from osteoporosis. Also, we have the family of hydroquinone, which is also an inhibitor, and also we have the quinones, which are used as inhibitors. So we have to know that if we have oxygen in the medium, the hydroquinone can react with the oxygen and will have formation of quinone. So we have inhibition, higher level of inhibition in the medium. Some nitroaromatic derivatives are also used as inhibitors for vinyl acetates, but are used as retarders for styrene. For example, nitrobenzene can act as inhibitor for vinyl acetates, but retarders for styrene. Some other nitroaromatic derivatives act as inhibitors and retarders at the same time. So example of this, we have the nitrosobenzene. So in this case, or in the case of presence of nitrosobenzene in the medium, we'll have delaying in the time on the starting of the polymerization where it acts as inhibitor, and then we have decrease in the polymerization rate as it acts as retarder. So there is no universal inhibitor or universal retarder. We should always consider the inhibitor or retarder and monomer couples, the combination of both. See you next time.